So we're looking at techniques of derivatives. We just got into this. So instead of using the formal definition of a derivative, using the limit, we're now going to start using these techniques to take the derivative. So it's a lot faster way to take the derivative. And so these were a couple of rules that we looked at or started to see last class period. So the derivative of a constant, if you just have a constant, that's always equal to 0. If you have f of x is equal to x to the n, where n is a real number, then when you take the derivative, basically you're taking your power n, bringing it down in front as your coefficient, and then subtract 1 from your exponent, and that is our derivative. We saw that if you have two functions that are added or subtracted together, so basically we can think of a polynomial of multiple terms, maybe like 2x plus 1. We can think of 2x as a polynomial f of x, and we can think of 1 as a polynomial g of x. And so basically we can just take the derivative, those are both differentiable. We can take the derivative of the first term plus or minus the derivative of the second term. And then the last rule we saw, that is if you have a coefficient in front of that, x to the nth power, then you basically can take the derivative of x to the nth power and multiply it by that constant in front. Okay, so let's just jump in. And then we also talked about the importance of rewriting things sometimes so that we could use this general power rule. And we looked at some rules of exponents and radicals, rewriting those as exponents. So if you had, for instance, y is equal to 8 square roots of x plus 6x to the 3/4 power. So find the derivative of the following. So another way to say that is dy dx or y prime. So if I take the derivative, oops, actually before I do that, let's rewrite this so that we can use the general power rule. So right now I don't know how to take the derivative of the square root of x, but if we rewrite this in exponential form, we have y is equal to 8x, the exponent is 1/2 plus 6x to the 3/4. Now that I'm taking the derivative, I'm putting this dy dx is equal to 8. So rule says take your exponent, bring it down front. So 1/2 times x. Take that exponent, which is 1/2, and subtract 1 from it. So when I have my exponent and it's not a whole number or integer, and it's a fraction, when I write my 1, I'm going to write my 1 so that it has a common denominator. And so instead of writing 1, I'm going to write it as 2/2. And then, so that's the derivative of the first piece, plus 6 times. So derivative of the second piece, again, you're going to bring your exponent down. So we're going to bring down that 3/4. And then x to the 3/4, and then we're going to subtract 1 from that. But I'm going to write 1 with a common denominator, so I'm going to write it as 4/4. So dy dx is equal to, well, let's simplify, 8 times 1/2 is just 4. X, and then 1/2 minus 2/2, that's a negative 1/2. Plus, and then again, let's simplify here, 6 times 3/4. Well, 6 and 4 both have a 2 in common. So we can say, well, 2 goes into 6 3 times, and 2 goes into 4 twice. So that coefficient in front of the x left is 3 times 3, which is 9 for our numerator, all over just 2. X to the 3/4 minus 4/4 is a negative 1/4. So usually we don't like negative exponents, and we can rewrite them so that they're positive exponents. Let me just see how these are written in here. So this was actually kept with the negative exponents. Well, they did it both ways. So let's just rewrite it just to get practice. So if you have a negative exponent, it's a single term right here, we're going to bring just the piece that has the negative exponent down to the denominator. So the 4, that negative 1/2 is not to that 4. So I'm going to keep the 4 in the numerator, and I'm going to put it all over x to the 1/2. Plus, same idea here with x to the negative 1/4. This has a negative exponent, so I'm going to bring it down to the denominator. So technically, I can think of this as over 1 right now. And so we'll have a 9 in the numerator, all over 2x to the 1/4 power. I'm going to write it one more way, just to get practice again. So if we have a rational exponent, we can rewrite this as a radical. And so we have dy dx is equal to 4 all over. So when you have a rational exponent, it's the denominator is what you're taking the root of. So we're taking the square root. So usually with square root, you don't put the 2 there. X. And this numerator is the power. So plus 9 all over 2. So x to the 1/4 power. So we're going to rewrite it in radical form, and that 4 is the index, or what root you're taking. So we're taking the 4th root of x. Okay, so they're all equivalent answers. So if you're given, how about f of x? This is equal to x cubed plus 5 all over x. It wants us to find the derivative. So let's say find f prime of x. So unfortunately, we don't actually know how to do this yet, or we don't know how to do it yet in the way that it's written. There is what is called the quotient rule. So if you have a polynomial divided by a polynomial, or you have a rational function, then we just can't take the derivative of the top, and we can't just take the derivative of the bottom. It doesn't equal that. And we'll look at that later. So we have to manipulate this so that we can rewrite, we can take the derivative. So notice that we only have a single term in our denominator, so we could actually break this up as 2 separate fractions instead of 1 fraction. So let's start by doing that. So this is the same thing as x cubed divided by x plus 5 divided by x. So sometimes it's helpful to split a single fraction up to a sum or difference of simpler fractions. Notice x cubed over x, that simplifies, so I'm using my rules of exponents. So if you have the same base, just a single term like this, they have the same factor of x, so we're going to subtract the exponent. So this would be 3 minus the 1 exponent, so this is really just an x squared. Plus, and this 5 over x, again, we're having problems because it's not in that general power rule form. But we can rewrite it, again, using rules of exponent. We can bring this x to the first power up to the numerator by changing the sign of the exponent to -1. So we have 5x to the -1 power. So now we can use that general power rule. So f prime of x is equal to, so bring down the 2 in front, so we get 2x, subtract 1 from our exponent, so 2 minus 1 is 1, plus 5 times our exponent, -1, x to the -1 minus 1. This gives us 2x, 5 times -1, so really -5, x to the -2 power. And then let's just rewrite it with a positive exponent. So the derivative of f of x is equal to 2x minus, it's just the x to the -2 that's coming down to the denominator. So 5 all over x squared. Okay, so here's another one that's kind of similar, but maybe a little more difficult. So what if it was g of x? This is equal to x cubed minus 4x all over the square root of x. It wants you to find g prime of x. You guys want to see if you can do it first? Such enthusiasm. It's because you're muted. You guys were all saying yes, right? Any ideas on how to start it?
Do we separate it like we did the other one into 2 fractions?
Okay, so let's do that first. And so if we do that, we have x cubed all over the square root of x minus 4x all over the square root of x. Now what do you think? So if you have a radical, this could be rewritten in without the radical and with a rational exponent. So this is x raised to the m over n power. So that's something that we'll use. And then there's also a rule that same base division. Like this, we could subtract, take the exponent on top minus the one on the bottom. There's just some some rules that we were using and just to put up there if you didn't remember them. Okay, so same, we need to use where we have to rewrite this as a radical. This radical, sorry, with a rational exponent. So this would be x to the 1/2 power minus 4x all over x to the 1/2 power. So rules of exponents. So this is, oops, shoot. I don't know where it went. That's one thing that's a pain on this program. Sometimes things shoot away and I don't know where they're at. There it is. Okay. So we're going to use that rule of exponents. We have x cubed minus 1/2 for the exponent minus 4x. So this is really a first power. So 1 minus 1/2. We need a common denominator so we can add those exponents. So 3 over 1. So this is the same thing as 6/2 minus 1/2 to get a common denominator. So 6/2 minus 1/2 is 5/2 minus 4 x to the, so 1 minus 1/2 common denominator. So 2/2 minus 1/2 is 1/2. Okay, so this was just to get g of x in the form so we can now use the derivative rule. And so taking the derivative, g prime of x, all you're doing is bringing your power down front. So bring the 5/2 down, x, take your power and subtract 1. But we're going to make that 1 minus 2 over 2. Minus 4, bring your power down front. So times 1/2, x, take your power 1/2 and subtract off 1. So I'm going to write it as 2/2. So g prime of x is equal to 5/2 x to the 3/2 power minus 2 goes into 4 twice. X to the 1/2 minus 2/2 is negative 1/2 power. Okay, so let's just rewrite this a little bit. Since we had started with a radical and it was in the denominator, let's rewrite this one. Did I rewrite the other one? No. So let's bring that down to the denominator to make that exponent positive. And so this is equal to 5/2 x to the 3/2 minus 2 all over x to the 1/2. But again, that was a radical, that was a square root. So we have 5/2 x to the 3/2 minus 2 over the square root of x. I want the cool little box. So a lot of the problems in this section is being able to manipulate this so we can get it in the form so we can use that general power rule. If you had x squared minus 1, and then that's all in parentheses, and then that quantity is cubed. So we'll learn a rule where we can just go ahead and just take the derivative of this, but right now we don't know that rule. And so we don't know how to do this because of this parentheses out here and that quantity cubed. So we want to rewrite this. So this is the same thing, and I can't just cube each term because there's more than one term in there. So I have to rewrite this as x squared minus 1, all times x squared minus 1, all times x squared minus 1. Unfortunately, if you're taking a derivative of a product of two functions, it's not the same as the derivative of the product of the derivative of each function. There's a product rule. We don't know that one yet. So what we have to do is we have to expand this. So we have h of x. This is equal to x squared times x squared, x to the fourth. X squared times negative 1, so minus x squared. Distribute our negative 1. So negative 1 times x squared is negative x squared. And negative 1 times negative 1, this gives me a plus 1. So that was just the first two parentheses multiplied out, all times the third one, x squared minus 1 up there. So let's just combine like terms before we distribute again. So we have x to the fourth. We have a negative x squared minus an x squared is minus 2x squared plus 1, all times x squared minus 1. So we got to distribute each term in the first parentheses to each term in the second parentheses. So x to the fourth times x squared. Rule is same base, add your exponents. So this is x to the sixth. X to the fourth times negative 1 is negative x to the fourth. Distribute the negative 2x squared. So negative 2x squared times positive x squared is negative 2x to the fourth. Negative 2x squared times negative 1 is plus 2x squared. And then distribute the 1. So 1 times x squared, so that's plus x squared. And 1 times negative 1 is minus 1. So before we take the derivative, let's combine like terms. So we have a negative x to the fourth minus 2x to the fourth. So bringing that down, we have x to the sixth minus 3x to the fourth. And then we have a 2x squared plus a 1x squared. So that's going to give us plus 3x squared. And then we have our constant, bring down minus 1. Now we can find h prime of x. Bring our power down front. X, take our power and subtract 1. Minus 3, bring our power down front. X to the fourth and then subtract 1. Plus 3, bring our power down front, which is 2. X to the second minus 1. And then the derivative of a constant. Remember, a derivative of the constant is 0. I'm just going to put that 0 there, so hopefully you remember.
0.
Is there a question, or are you just helping me out? Thank you. So 6x to the 5th minus 3 times 4 is 12. X to the 4 minus 1, so x cubed, plus 3 times 2, so plus 6x. Okay, so we're just kind of doing mechanics. So it's just really, following a rule, like order of operations of simplifying expressions, or so we're just doing these mechanics to make life easier when we want to take the derivative. But we can apply what we've been doing before. So we've had questions like this before. So find the slope of a tangent line to the graph of a given function at the given value of x. So find the equation of the tangent line. So for example, let's say you have y is equal to negative 3x to the 5th minus 8x cubed plus 4x squared. So I'm going to find the equation of the tangent line. At x equals 1. So we need a couple things. We need to know what the slope of this function y is at x equals 1. We need to find the slope of y at x equals 1, which is basically the slope of our tangent line. And we need to find the point on the tangent line. And then we have to find the equation. So to find the slope of the tangent line, how are we going to do that at 1? So just for notation wise, it would be easier if we just call this f of x, which is another way to say y. So let's first take the derivative of f of x. So f prime of x, we're just going to use the general power rule. So we have that negative 3, and we're going to multiply by our exponent, which is 5, x, and now we have 5 minus the 1 power. Then we have a minus 12. Taking the derivative of x cubed, bring our power down front, which is 3, x, and take your 3 and subtract 1 from that exponent. Plus 6, bring our power down front. Well, if the power is not shown, it's 1. And this is x raised to the 1 minus 1 power. Oops. Oops, I took the wrong thing. I was taking the derivative of partly my function h of x up there and partly my f of x here. I took the derivative of my first term, okay, negative 3x to the 5th. But the last two terms were the function above. Sorry about that. So the second term for f of x is minus 8x cubed. So we'll have the minus 8, taking the derivative of x cubed, and bring down our power of 3. X, and take our power, which is 3, and subtract 1. Plus 4, bring our power down for the x squared, which is 2, and subtract 1 from our power. So this gives us negative 15, x to the 4th power, minus 8 times 3 is 24, x squared, plus 4 times 2 is 8, x to the 1st. So this is giving us the slope where we can find the rate of change any place on our graph of f of x, but we want to know what's happening at x equals 1. And so if we look at this at f prime of 1, so we're going to go up into our equation f prime of x, and wherever we see an x, let's put a parentheses, and then we're going to replace it with 1. So we have negative 15, parentheses, to the 4th, minus 24, parentheses squared, plus 8, parentheses. So I have negative 15 minus 24 plus 8. Negative 15 minus 24 is negative 39. Negative 39 plus 8 is negative 31. So right here is our slope of our tangent line at x equals 1. So now we need to find the point on that tangent line. So how are we going to find that point on the tangent line? We got our equation. Our tangent line is going through that point on our graph of f of x at 1. So we need to figure out what is that point on that graph when x equals 1. And so we want to plug in 1 into the original function. So if we look at f of 1, this is equal to negative 3. You see an x there. Put a parentheses, we're going to raise that to the 5th, minus 8. You see an x there, put parentheses, we're going to cube that, plus 4. Have an x there, we're going to put a parentheses and then square it. So we got negative 3 minus 8 plus 4. So negative 11 plus 4. That gives us negative 7. So our point is at x was 1. Our y value we got back was negative 7. So y is equal to our m value times our x value plus b. Put in what we have. Y is negative 7, which is equal to our slope, which we found was 1, times x, which we were given was 1, plus b. So we have negative 7 equals 1 plus b. Let's subtract 1 on both sides to get b by itself. So b is negative 8. So knowing our b value, knowing our slope of the tangent line. Oops, something's wrong. Our slope, I was looking at x equals 1, is actually negative 31. So we need to plug in negative 31 instead of negative 31 here. So negative 7 is equal to negative 31 plus b, so we're actually going to add 31 to both sides. And so that would give us 24. So b is equal to 24. Okay, so now knowing b, knowing our slope, we have our equation of our tangent line. Y is equal to our slope, negative 31 x plus b, which was 24. Okay, so we've done that before in the past. We just would have had to use the limit. And that would have just been really crazy and ugly with all those exponents. Okay, so the next example is what's going to really help us actually when we go more to the applications. So basically, again, we're looking at the rate of change, what's happening at a particular value of a function. And so what is happening to the rate of change of our profit or revenue as things happen with production? How can we maximize profit? How can we minimize cost? So knowing max and mins, recall if we're looking at a graph and we had some function and we were looking at where the slope or what the slope was at particular points, right? We would look at the tangent line and we would find the slope at that point. We talked about how it was kind of looking like it's your car driving with the headlights pointing where you were at. So here, we have the slope like this. So for maximum values, notice that our slope of our tangent line is horizontal. And a minimum value, if we're looking at the tangent line, that tangent line is horizontal. And so the slope of horizontal lines is 0. So if we can find when the derivative is equal to 0, it will help us with techniques to find if that's a max or a min value at that point, and then we can use it. So this next question is saying, for each of the function, find all values of x where the tangent line is horizontal. And that's the reasoning behind why we will want to do that, finding max and mins. So if we had f of x is equal to x cubed minus 5x squared plus 6x plus 3. So find where f of x has a horizontal tangent line. So again, we want to see, we need to find when f prime of x is equal to 0. So this one isn't too bad to take the derivative. We're just going to use the general power rule, bring our power down front. So for x cubed, bringing the power down, we have 3x, subtract 1 from the power is a square. Minus 5, derivative of x squared, bring the power down front to x. Plus derivative of 6x is just 6. And the derivative of a constant is 0. So we have 3x squared minus 10x plus 6. So we have 3x squared minus 10x plus 6. We want to find when is this equal to 0. So looking at what type of equation it is, it's quadratic. Different ways to solve quadratic equations. We could try factoring, which if it's possible, sometimes is the fastest and easiest. We can complete the square on this, which could be kind of tedious at times. And there's the quadratic formula, which is basically the condensed formula of completing the square. I don't see that this is factorable. I'm just gonna go straight into completing, not completing the square, the quadratic formula. So just recall, let me just give you that. So if you have ax squared plus bx plus c equals 0, x is equal to negative b plus or minus square root b squared minus 4 times a times c all over 2a. So all I'm doing is I'm just going in here and plugging in my values and simplifying. So I have x is equal to, so b, negative b. So negative of negative 10 plus or minus the square root. Again, I see b here, so I'm going to replace it with negative 10. Tells us to square it, minus 4 times our a value. Our a value is 3 times 3 times c. There's c values. Is 6 all over 2 times a. So negative 10, positive 10 plus or minus the square root. Negative 10 squared is 100, minus 4 times 3 is 12, 12 times 6 is 72. 72 all over 6. So x is equal to 10 plus or minus square root minus 72 is 29. 6. So this can be reduced. There's a factor underneath the radical. That's a perfect square. So kind of side work over here. Square root of 28 is the same thing as the square root of 4 times 7. Square root of 4 times the square root of 7 is 2 root 7. So plus or minus 2 root 7 all over 6. So we can simplify. We could pull a 2 out of the 2 terms on top so that it can simplify with the 6 on the bottom, so that it's in factored form. So if we pull 2 out of the top, 2 out of 10 is left with a 5, plus or minus. Pulling a 2 out of the 2 root 7 is just root 7 all over 6. 2 goes into 6 3 times, 2 goes into 1 twice, sorry, 2 goes into 2 once. So x is 5 plus or minus root 7 over 3. Okay, so there's 2 places that you would find that the graph is horizontal. And that's going to be when x is equal to 5 plus root 7 all over 3 and 5 minus root 7 all over 3. So let's just go to Desmos real quick. Let's graph that function and let's show that our values at 5 plus root 7, so let me just estimate what that is. Root 7. I'm going to divide that whole answer by 3. We get approximately 2.55. And if I do 5 minus the square root of 7, take that result and divide it by 3, we get about 0.78. Okay, so we were just graphing y equals, well, we weren't graphing. We just took the derivative of y equals x cubed minus 5x squared plus 6x plus 3. And then we were asked to find when is the graph of this function have horizontal tangent lines. And I told you that, you know, that was going to be where probably we hit a max or a min. And so if I put my cursor here and I click on this, notice what value I get, 0.78, that x value that I said, you know, if I, whatever it was. But the estimated was that, and then this one is going to be 2.5, and I rounded it up to 5 because of the 9. So we found the x values right here where we have max and mins on that curve. Okay, so let's pause. So we're going to look at a couple more examples from this section, and then we're going to watch a video from 3 Blue, 1 Brown on the interpretation of the derivative with geometry. And gives you kind of another perspective of looking at things. So for each function here, let's see, we're given the following. So let's say that you are given that g prime. Sorry. Again, we're given that g prime of 5 is equal to 12. And h prime of 5 is equal to -3. Find f prime of 5 for f of x, which is equal to the following. 3 times g of x minus 2 times h of x. Actually, you know what? I don't even know how to do this problem. 3 times g of x minus 2 times h of x. Okay, let's see if we can figure this out. Sorry, I thought that this would have said f was 3 times g prime. And so I'm off because this is not. It wants us to find f of 5. Can we think about this? Because we're, oh, duh. Okay, this is not bad at all. So we want to find f prime of 5, right? And so we need to figure out, let's find f prime of x. Okay, so if we're going to find f prime of x, we're going to go through here and we're going to take the derivative of this whole thing. And so f prime of x, this is going to equal 3 times the derivative of g of x minus 2 times the derivative of h of x, which is h prime of x. And the derivative of a constant is always 0. Now we want to figure out, find f prime of -5. So we're going back up into this equation, and wherever we see an x, we're going to replace it with -5. And so we have 3 times g prime of -5 minus 2 times h prime of -5. And I don't need to add that 0. But we're given what g prime of 5 is. Actually, it wasn't -5. Sorry, it was just 5. But we already know what g prime of 5 is. That is 12 plus or minus 2 times h of 5. And we're also given what h prime of 5 is, which is -3. Let's just simplify this. We have 3 times 12 is 36. -2 times -3, so this is +6. So this is equal to 42. So f prime of 5 is equal to 42. What I want to go through. So I think from there you should be good with seeing examples from like the homework. Okay, so I'm gonna stop the video. We're gonna watch the video. I'm not gonna tape it. Um, I will leave a link for you on my Canvas page. So if you didn't come to class and you want to watch it or make it up, you need to go to this video and watch it. And then after the video, we'll come back and kind of talk about what you guys think and call it a day.